Hello, I'm Pam Hoffman, Everyday Spacer.
I'm Jeff Miller, 2049 Outfitters.
At Everyday Spacer, we show regular folks how to personally and directly participate in space exploration, science, and astronomy. We're here on Friday nights at 9 p.m. Pacific Time, 12 midnight Eastern Time, and 4 a.m. on... Nope, I didn't check that one. I don't know if it's 4 or not. I know this one at 1 p.m. on Saturday in Hong Kong. We had a time change. We're broadcasting live from Thousand Oaks, California.
If you like this video, please subscribe and hit that like button. Thank you.
Tonight, we're going to have a crunchy topic. What's the matter with antimatter? We'll be back in 8.3 seconds. In tonight's episode, we will be talking about antimatter. In the past, we have gotten a lot wrong with antimatter, from thinking that it moved backward in time, thinking that it had anti-gravity properties, to thinking that it would be a great energy source. Jeff, tell us, what's the matter with antimatter? And before we do that, why don't we say hi to our guests?
Yeah.
We have a couple people.
Jamie.
Hi, Jamie. Happy Veterans Day weekend to you, too.
Yep. And Cliff. Hey, Cliff. And
3 p.m.
3 p.m. in Queensland.
I knew that one because I checked.
Yep.
Jeff, antimatter.
Okay. Here, let's get to... Here, very simply, that's matter, that's antimatter. Basically, it's... Oh, hey, Scott.
Oh, Scott.
Antimatter is about the crunchiest topic I can think of. Yeah, and I saw an Anton video, and that made me think about something.
Yes.
Made me think about something that I saw about antimatter before, too. So it kind of was a bunch of different things.
All right. Hey,
Don.
Welcome. Thanks for joining us, everybody.
Yeah.
We really appreciate that. Can you bigify that a little bit? It looked like a bunch of M&Ms.
Oh, okay. Yeah, here, let's go over here. Yeah. First off, F11, and then
kind of...
They look like Skittles to me, but... There we go.
Well, what's the main difference?
It's the quarks.
It's the quarks. Okay.
Yeah.
Oh, quarks and anti-quarks. Okay.
Yeah.
Interesting.
Yeah, and yeah, let's just get this going. Hey, there we are. Okay. Yeah, there's a couple things that we've gotten wrong in the past. One, very early on, Richard Feynman and a bunch of the early guys, and I saw this doing profiles of Feynman and his sister, is they thought that antimatter went backward in time. And
do you know why they thought that?
Well, because the particles behave as if they're going backward in time.
Ah, okay.
And that initially made people think that they actually went backward in time. But it's more like an ice skater who does right-hand spin. Then she does a left-hand spin. The left-hand spin is as if she was doing a right-hand spin backward in time. So it looks like a right-hand spin backward in time. But she's still going forward in time. Okay. You know, if she was moving in a line while spinning, she'd still be moving in the same line, no matter which direction she spun.
And what came to mind when you said that was, you know how you see something spinning and all of a sudden it looks like it's going backwards?
Right.
It isn't actually.
Well, that's our brain, yeah.
But still, it gave me that same idea of, well, we see that in particular cases when something is spinning, and it's probably a frequency thing, right? I don't actually know.
Yeah.
But
and spin isn't really what's going on there. Yeah. It's just a good analogy.
Yeah, it just made me think about that. That's all.
Yeah.
Where we see it spinning, and then all of a sudden it looks like it's going backwards.
Right. And the fact that the Feynman equation, which, hang on, let me pull it up here, and I'll switch to it once I find it. Here. It's one of these.
You ready?
No. Hang on. These are running. These are playing. Um,
We'll share screen in a moment.
yeah.
They
There
all
we
look
go.
good.
There we
Okay,
go.
ready?
Yeah.
Okay, here it is.
Yeah. Okay. So this is the Feynman diagram that, oh, you want to bignify it?
Yeah, if you can.
Yeah. Let's see what we can do with that.
Looks pretty small.
Yeah.
Yeah, you may recall seeing these before.
Yeah, when we talked about Feynman,
Mm-hmm.
you know, this was one of his big things, is that an anti-electron gets whacked by a photon, turns into, or an electron gets whacked, turns into an anti-electron. And it works backward too.
Got it.
And the main thing is that when they originally said that, it acts as if it went backward in time, people took that to say that it actually goes back in time. In fact, Feynman actually, I think he either believed it or he was joking, because there's a quote.
Could be either way.
Yeah, there's a quote attributed to him that it may be his or it might be of colleagues of his, but he's credited with it, and there's no real evidence otherwise, and he's just a bigger name, so he probably, but he repeated it. So but he said that as a thought experiment, there might only be one electron.
Okay.
That it can go forward in time and back in time, forward in time, and so we'd have an electron, anti-electron, so they could all be the same electron. I don't know if he was serious when he said that, but interesting thought experiment, except for then where are all the anti-electrons? If that was doing that, then it would be, then you'd have the exact same number of anti-electrons as electrons. So that's just not likely to be happening.
Okay, I don't really know what anti-electron is, but okay. When I was in school, we called them electrons versus holes.
Positrons.
No, we called them holes, but that was just.
Oh no, that's something different, actually.
Yeah, it was just a useful way to understand how electrons flow through circuitry.
But that's not actually an anti-electron or a positron.
Okay.
That's just a space of no negative charge.
Yeah.
So a positron, so they basically determined that no, it doesn't actually go back in time, even though the particle behaves like an antiparticle behaves like a regular particle, as if it was going back in time.
Okay.
But it's still going forward in time.
Okay.
So, but you can still see every once in a while, you see something saying that they go backward in time. But they've shown that they don't. Another thing that that we've seen is
he's scrolling around. I'll wait.
Yeah, that I'm finding. Oh, they changed that. Okay, the gravitational interaction of matter.
Am I sharing? Are you ready?
Yeah. Okay. We lost this. Okay.
There it is.
Yeah. One of the things, and I saw this on an Anton video, and why don't you pull it to both? An Anton video talked about how there was a theory that antimatter was anti-gravity, which would have explained an awful lot. Because if antimatter was anti-gravity, then when the original universe was created, that antimatter would have flung away from the matter. They basically would have repulsed each other.
Okay.
So you'd have matter in one direction and antimatter in the other, which would explain why everything that we can see out to the limit of how the speed of light is matter.
Matter, yeah.
Because there could be just as much antimatter over there
somewhere else, yeah,
as there is matter here. And it very much solves if matter and antimatter are created equally, why is there only matter? So that
Okay.
was, so that was a good solution to it. And there was never any real physics behind it. It was a good explanation. And they spent a long time with the physics trying to figure it out. And they've pretty much stated that no, mass is mass. There isn't, except mathematically, there is no such thing as negative mass.
Okay.
It's just
imaginary mass.
Yeah, it's a mathematical construct that doesn't exist in our universe. Okay. But there wasn't any proof of that. And so they started doing an experiment.
Is that what the picture is?
Yes. Here's the experiment right here. What they did was they collected antihydrogen, which basically they created a positron and an antiproton, and basically let them collect each other into an atom of hydrogen. And they contained them in a vertical cylinder and held them magnetically, and then basically then created a magnetic field so that everything would be suspended.
Magnetic bottle, basically.
Right.
It holds it in place.
Right. But countered gravity by making the magnetic field counteract gravity just to be equal, and held them in place in the center.
Okay.
And what they did then was they took the top and bottom off of the magnetic bottle, because if matter was anti-gravity, it should essentially spew out the top, since there was no gravitational force, in quotes, acting against it, because the magnetic field was counteracting it.
Okay.
If there was gravity, then they should come out the top and bottom equally. Because they're counteracting gravity, so the only force that should be coming to them is just the natural repulsion against each other. If they all poured out the bottom, then something screwy was going on, because they accounted for gravity, and anti-gravity would be coming out the top. If they all came out the bottom, WTF, which would probably excite the heck out of them, because it would mean that they got something that they totally didn't expect.
Yes.
But
that doesn't always excite people. Sometimes they're very upset about that.
Right.
Michael Morley.
Yeah.
For example.
Yeah. Well, then they start trying to explain how their experiment failed. But yeah.
I think you had a chart about that, right?
Yeah.
That it acted just about like regular matter.
Right. Yeah. Yeah. And then there's a chart down here. Hang on. Lots of charts. I'm going to send a link to this article. This is the article where they do that.
Oh, it's
Here's
very
the
long.
escape curve. Yeah. So this is the curve. The line is where normal gravity simulation. So this is how things should have escaped. If there was no gravity, so say it wasn't either affected by gravity at all, then it would come out on this green curve.
Okay.
And if it was anti-gravity, it would have come out on this curve.
Kind of purple color.
Yeah. And all of these data points here are the actual experimental data.
Oh, some are kind of in between.
Right. But they're fairly close to this one. Now, and here's the thing, is that they don't have a huge amount of data.
Okay.
Because antimatter is really expensive to make, and even more expensive to store.
Yes. So
they're continuing to do this experiment to refine their results.
Okay.
But if it being between, if it doesn't basically bring itself up to the line of normal gravity, then there is something going on.
Okay. Interesting.
But
and that the top is the normal gravity.
Yeah.
Kind of an orange.
Yeah, the orange line is the normal gravity. So I would expect with more, my expectation may not be true, is that as you get more data, it'll move itself up to the orange line. Now it could very well move itself down.
Mm,
because, while they have a number of data points, they don't have a huge amount.
yeah.
So,
And it does look a little bit inconclusive because.
right. Well, except that you'd have to get all the way down here for it to be
Oh, I see.
anti-gravity.
I see. Right. Yeah.
The green line is gravity has no effect on it whatsoever.
Mm-hmm.
Um,
So right now it's sort of between normal gravity and
right.
not really.
And gravity not affecting it
Mm-hmm.
is would be an unexpected result
Mm-hmm.
because it would have mass or anti-mass.
Mm-hmm.
I mean, would antimatter have no mass? I don't think so. It's a possible result. Who knows? But that's, it's not one that I would expect. So I would expect that it would keep refining to normal gravity simulation.
Okay.
But
Interesting.
yeah. So nope, which means that we're still stuck with why is there more matter than antimatter?
Alternative universe.
Yeah. And here's one. The universe is much bigger than we think. And it's clumpy. And we're just in a clump of matter. And there are clumps of antimatter.
Interesting.
With maybe zones of annihilated, of nothing in between them. Because they annihilated each other.
Okay.
But our clump is just big enough that the speed of light limit means that we can't see the clumps of antimatter or other clumps of matter.
Okay.
I mean, it's a thought experiment that there's no way to actually prove that. I think
not currently. I think
unless you can possibly measure the entire curve of space, you might be able to determine whether there's matter past our light limit. I don't know. That's higher level math than I can get into.
Okay.
But so no backward in time, no anti-gravity, which would have been neat because you could have you could have floated
like
off the ground if you'd created
just
enough
paint some on the side you want.
Well, except that then the side that you want turns into gamma rays.
Okay.
Matter antimatter do not really mix well.
Oh, I see.
Yeah.
Because you're painting your
your
spaceship that's matter.
Yeah, it'd be difficult. Which
you need to hold a magnetic bottle and push it out, maybe.
Right. Yeah.
Oh, hey, Scott. But if there was a clump of antimatter out in space, how would we know it was antimatter and not just matter?
Throw something at it.
Throw some matter at it and see what happens. If it annihilates each other.
Right. Yeah. And note that it won't, like throwing a pebble at a planet of antimatter will just make a boom in one localized spot. So possibly theoretically there could be galaxies of antimatter, maybe even a star of antimatter in our universe. However,
would we be able to see it?
Yeah,
we would. Okay.
Sure, because everything that they've shown, all of their experimentation shows that antimatter works just like matter as long as it's only interacting with antimatter.
Okay.
Interacts with photons, interacts with, so antimatter is not dark matter. Okay. Because photons react to it. Okay. So that's not that explanation either.
Wow.
So there's a lot of stuff that antimatter isn't.
Okay.
But, and if there was a star out there that was antimatter, what did it come from? I mean, was there a whole gas cloud of antimatter? And if that gas cloud hits another gas cloud, we don't see, we don't see that. We don't see the interactions there. So not likely.
Are the stars perhaps a combo of matter and antimatter?
No, because...
No? Okay.
Yeah, no, again, it would look different than a current star.
Okay. Because
antimatter just basically matter essentially produces gamma rays.
Okay.
And
there are some out there though.
Yeah. We just don't have stars that do it like that. I mean, it would have a different signature. Oh.
Would sunlight from an antimatter sun be regular sunlight?
Yes. Yes, because a photon.
Okay, all right.
A photon is a combination of electron positron. Basically, when they annihilate, they create a photon.
Okay.
And that photon can in certain circumstances, break back up again.
Mm.
And so you can create antimatter and matter, and then the photon comes back together again eventually if they hit each other. So yes, the sunlight would be normal light, and that's the thing about antimatter, is that it works just like matter. As everything that we've seen, all of our experiments so far, and this one about the gravity, again, it works just like matter for everything that we've been able to test.
As long as it doesn't mix with matter.
Right, yeah, then it goes boom.
Yeah.
Actually, determined what would happen if you took a person from an antimatter universe and teleported them onto the Earth. What would happen? Well,
sounds bad.
Really big boom. Actually, multiple big booms.
Okay.
Because the surface would explode.
Surface of the person?
Yeah. Because that's the only part that's interacting with the matter.
Yes.
However,
until you get down to the next
right. So it'd be a series.
layer
Basically, it would
of
blow the matter away.
molecules.
As soon as it comes back, boom again. However, after that first boom, all of the limbs and head would be flying in different directions. So then you've got a shotgun effect of more booms.
Holy mackerel.
As it breaks up, you'd get booms spreading out all over the place.
That sounds really bad.
Yeah. The experiment, no, this was for a D&D game.
I see.
So, and we were nerds, so we actually calculated it out.
Okay.
If you put a force field around it, a cylindrical force field, it becomes a crust punch.
What?
You punch down to magma.
Oh, I see.
Doing that.
Okay. All right.
Yeah. Which actually makes things worse.
It sounds horrible.
Don't
do that. Don't build that. Don't do this at home.
This is what you get when you get a bunch of nerds who are interested in physics.
They did this for 20 years. They met together for 20 years.
Yeah. But this was when we were still in college.
Okay.
So, yeah. So don't do that. Yeah.
Don't try this at home.
And that also brings into another thing that's the matter with antimatter. What's the matter with antimatter?
Mm-hmm.
Is that people are talking about it as this great source of energy. Think of it like hydrogen as an energy source, except worse. Takes a lot of energy to produce.
Yeah.
Takes more effort to contain.
Yeah.
And then you just don't get all of that out of it when you use it.
Well, there's always loss in a system.
Right.
No matter what it is.
But with antimatter, it takes an awful lot of energy to create it.
Okay.
It's just really expensive to create. Then you have to store it in a magnetic bottle. So far, I mean, there might be other, super science ways of doing it, but we don't know any. So you have to store it in a magnetic bottle, which means that you're spending energy to do that.
Yep. Not just once. You got to keep it going. You got to keep it spinning.
Right. Eventually, if you store it long enough, you've spent all the energy that you're going to get out of it.
And more.
Just storing it. Yeah.
And more.
Yeah.
Eventually.
Yeah. And if you sneeze wrong, it blows up. I mean.
Crikey.
Yeah. So I look at the Star Trek stuff, antimatter energy. Don't really want to touch that stuff for that. Now,
that's in their engine, right? The warp drive or whatever.
Yeah, the dilithium crystals, which were their handwavium crystals, actually produce the antimatter.
Oh, I see. I didn't realize that.
Yeah.
It was a storage of antimatter that wasn't. Okay.
Yeah. So they don't actually store it; they produce it and use it right away.
Oh, I see. Okay.
But yeah, that's so unless there's, and if we have the sci-fi chops to store antimatter or create it without spending huge amounts of energy at it, we can use whatever we're doing to do that to just do whatever we would use the antimatter for.
Less loss.
The only thing the antimatter seems to be really good for right now is making a bomb.
Okay.
And we could do that.
We know how to do that. Clearly.
I wouldn't want to be on the airplane carrying that
No.
bomb, because one bad bullet could basically ruin your whole day.
Got it.
You know, so we'll see. I mean, there might be a use for it later. We might figure out why why we actually exist, because that's the problem with, if matter and antimatter are created at the same time equally, we would not exist.
Yeah, how'd that happen?
And
that it didn't all annihilate each other.
Yeah. One
because we're still here.
One theory,
Yes.
again, it's only math. There's no actual evidence that this happened.
No experiment either, I take
Right,
it.
yeah.
Okay.
Is that matter and antimatter we're not quite equal, down to the 1 to the negative 10 or 15. So 0.00, lots of zeros than a 1.
Okay.
That there was just slightly more antimatter, which means that the universe...
Antimatter or matter?
Or matter, yeah.
Okay, that's what I thought you meant.
That the
because we're still here.
Which means that the universe was humongously much bigger than it is now, and we're only the crumbs that are left. Basically,
great, we're breadcrumbs.
It created itself.
The matter that's left over after the annihilation.
Almost all of it, piffed again, and then we're what's left.
It must have been a hell of a lot if that's the case.
Right. And they say that producing that much of an imbalance might be within randomness.
Okay.
The trouble is that it might be, but it still goes against what we know of the way matter and antimatter are created.
Okay.
The way we, so I don't know. No one really knows. There's a lot of math to give evidence to either way, but all it is math. I mean, I made the joke about darkons when we were talking about dark photons, and the math works just fine if you're looking at optics, but it's just math, and physics says no. So,
okay.
So yeah, I would have liked antimatter to be anti-gravity. That would have been perfect because it would have solved an awful lot of stuff. But in some ways, it means that gravity is mass as mass, and there's no anti-mass, which also means that you're making warp drives. They've actually theorized warping space, but it requires negative mass. So,
which is
antimatter. As far but which is also but they don't have a source for anti-mass. It requires anti-energy, which is what?
Yeah.
That's
imaginary energy.
Yeah. So I don't think that, unfortunately, that's also not going to be a source of, of faster than light travel either. So, so many things, so many dreams die from reality.
Yeah, but so many of them come true. I mean, you look at the Star Trek from 1960s, and we're all carrying the little. I mean, we had flip phones for a while. Yep. Now there's iPads, and I've heard some noises about transporter things, and I mean, we keep developing bits and pieces of it. I mean, 3D printers are getting darn close to replicators, so who knows?
Yeah. Transporters, they can transport electrons.
Yeah, I read something about the Navy experiments in the 40s or something that went really bad.
Wow.
Like really bad.
I
just found an article about it.
Philadelphia experiment.
I don't know.
It's a science fiction movie.
Okay. This was I read an article, so.
Yeah, okay. I could write an article about it too.
Or maybe it was a Be Amazed. Was it a Be Amazed? Maybe it was a Be Amazed.
Yeah.
Maybe I have yet to see it. That's why I don't know much.
Yeah.
Don't know too much yet.
Yeah.
Those are interesting and bizarre.
Yeah. But
like the orange peels in the forest.
Yes.
That's actually really cool though.
Yeah, I do have a bunch of links for videos on antimatter and the
You had the Anton show, right?
Yeah.
Show us that one, because I know last time I referenced one, but I couldn't find it.
Yeah.
And Dawn asked about it, so let's see. What's it called here? It's
strong evidence that anti-gravity probably doesn't exist. And this is a CERN
experiment.
experiment.
That's from August the 1st.
No, October the 1st.
Oh, October the 1st, sorry, of this year.
Yep.
This year. So there you go, Dawn.
Yeah, and here, let me put it in here.
Oh, good. All right, that should be a clickable link in the chat for you.
In fact, I will grab the, and he references this article in Nature.
Oh, very cool. Oh, so you went and found it. That's good.
Yeah. Well, in fact, that's why, because I didn't want to just take his word for it. I took the word for the right, from the writers of the article, whatever.
Got it. Well, that's the thing. You find a number of different sources to.
Yeah.
It's called triangulation. You find at least 3 or more sources if you can. And I don't mean everybody's quoting the Wikipedia page. I mean this scientist and that experimentist and different people have written about it.
And
done things.
And so far, there aren't a lot of experiments about the lack of anti-gravity. So could be there was a flaw in that experiment. I mean, so it's not completely dead, but it looks dead now. I mean,
all right. Yeah, you put a bunch of links in there. So go look for those. They should be clickable in the chat.
And this last one that I'm asking about is the backward in time one.
Cool.
Oops. Hit the right key.
There you go. Looks like it went.
Oh, no, you know what? I need to put it on again because there's a character at the end.
So. Oh, I see. Yeah.
So.
Which won't make it clickable. Well, I don't know.
Yeah, I don't.
Might not make it clickable. So
yeah. So I'm gonna send it again.
Just do it again.
And can I delete those bad ones?
I don't think so. Don't worry about it.
Oh yes, I can.
Oh, you can?
The comment. Yeah.
Oh, we learned something.
Yeah.
All right. You have anything else to share with us?
No, I'm just going to clean out the ones that aren't clickable.
So while you do that, I will go into the stellar events for this week. And we're talking about November 10th through November 17th. I'm going to tell you first about the Globe at Night project, which continues. That started on November the 3rd. It goes for just a couple more days till the 12th. In the Southern Hemisphere, you can look for Grus or Pegasus. They've started this year where you have two targets. You have an option of 2 targets. Sorry. And in the Northern Hemisphere,
sorry about that.
You can look at Pegasus or Perseus. And I think if everybody looks at Pegasus, that would give them a more interesting result. Anyway, you go out, you look at the sky, you can take some pictures, report what you see on the site, Globe at Night. And we've shown that to you many, many times. So, just put in Globe at Night in a search. You will find it. Apparently, this is a pretty important project, though. So, I got my timer set every night, and I got to get out there. I have not done it yet. I will, though. November 11th, the moon is at descending node, and it's Veterans Day here in the United States. And I guess it's Remembrance Day in Canada and England, and possibly other places. We'll be celebrating our veterans. We had November 9th, but it looks like it might be 11th, 12th, the northern towards meteor shower peaks. And you want to look east after midnight. The moon is very small, though, so that's good. It's waning from last quarter, and it'll be new moon on the 13th. So that's a good moon to have for a meteor shower. On the 13th, like I said, new moon. Also, Mars and the moon are in conjunction, and Uranus is at opposition. And it's I read it was going to be in between two Pleiades and Jupiter. Pleiades and Jupiter, and it is something you can look at through your binoculars, and it appears kind of green. So, yeah, you might want to go out and look for that on the 13th, which, what day is that? That's Monday. Monday night. Take a look and see if you can see Uranus. It's at opposition. It's kind of the closest point at which it comes. We hit these every year. We hit all of them every year just because of the orbit of the Earth. All right, so November 14th, Mercury and the moon are in conjunction. November 16th, the moon runs low. And November 17th, we're back to Friday night show. I'm going to do another profile. Stick around, and I'll tell you who I'll talk about. Find us Fridays at 9 p.m. Pacific time on the Everyday Spacer Facebook page and the Everyday Spacer YouTube channel. November 17th and 8th, through 18th, the Leonid meteor shower peaks. That's going to be after midnight. The moon is only 4 days old, so still another good night for a meteor shower. It's a crescent, it's waxing, but it's going to set pretty early. Just about, we would decide 3.5 hours. So yeah, should be a pretty good night for a pretty good month for meteor showers.
Yep.
Thank you.
Cliff.
Oh.
Says that 11/11 is for
Remembrance Day.
Yep.
Okay, very good. Thank you for sharing that. I wasn't aware of that, but seems like it's kind of a worldwide, a lot of places in the world.
Well, at least
remembering
a lot of Anglo places.
Yeah.
You know.
Yeah, got it. Yeah, makes sense.
Okay, New Worlds Conference. www.newworlds.space. Not .com, it's .space.
I'll put that in there.
Okay, yeah. It's November 17th and 18th, 2023. Join astronauts, artists, and experts in policy, education, and human health discussions. It's physical location, so you have to go to the Bullock, Texas State Museum in Austin, Texas.
Yep. If you or someone you know has done something interesting involving space exploration, science, astronomy, I actually sent an email to Anton Petrov and invited him to be a guest on our show. Send up prayers. I would love to have him as a guest on our show. That'd be so fun. We would love to share our live. Join us again next Friday, November the 17th. I'm doing a profile of sci-fi author Andre Norton, and I created a trivia question for that. Is Andre Norton a pen name? All right, so anything else from you?
Nope.
Anything else from you?
Nope.
Let's give a shout out because our regulars are here again.
Oh, Scott.
Oh, you got another comment? Oh, good.
Scott. Yeah, thanks, Scott.
Thanks for joining us. Scott and Dawn and Cliff and Jamie. And I think I got everybody right.
Yeah, you got Dawn. Yeah.
Yep. I'm going to look for you tomorrow, Janie. So I know you got an event going. I'm going to try and be there. So, all right, folks. Cool. Have a really great week. Enjoy your Veterans Day weekend. And I will see you next Friday the 17th.
Yep.
Good night.
Good night.
Yeah.